We're talking about reaching for the stars, not with chemical fire and thrust, but with, well, essentially a piece of string that runs 100,000 kilometers into the sky.
By 1891, state-of-the-art presses were producing 90,000 four-page sheets per hour.
Okay, let's put that entire journey into one final perspective. Hand copying. A few pages per day. The original Gutenberg press. 240 impressions per hour.
Koenig's first steam press jumped that to 1,100 impressions per hour in 1814.
And by 1891, the rotary press was achieving 90,000 four-page sheets per hour.
That is a speed increase that truly restructured human civilization.
And that's the moment.
What moment?
The moment heresy stops being just a spiritual danger and becomes an act of treason against the Roman state, a precedent that would last for centuries. Welcome to the Deep Dive, the place where we take the world's most audacious concepts, grab the blueprints, and really figure out if they're on the cusp of a breakthrough, or if they're just firmly in the realm of perpetual science fiction.
And today's concept is a big one.
It is. Today, we are attempting to replace the rocket entirely. We're talking about reaching for the stars, not with chemical fire and thrust, but with, well, essentially a piece of string that runs 100,000 kilometers into the sky.
That's right. We're tackling what may be the greatest, most challenging infrastructure project ever conceived, the space elevator.
Sometimes called the skyhook.
Right.
Or even more dramatically, a star ladder.
A star ladder or an orbital lift, yeah. It's a structure that would just fundamentally redefine our entire relationship with gravity and space access itself.
The idea, the mythology of it is just so captivating. An actual fixed line connecting the surface of the Earth directly to a stable point in orbit. It promises reusable, predictable, and incredibly cheap access to space.
That's the dream.
And our mission today is to unpack the reality of that dream. We're going to dive deep into the, frankly, bizarre physics that keeps the whole thing standing up, the architecture you'd need to build it, and the immense, currently unsolved material science hurdles this project faces.
So for anyone who wants a serious, a comprehensive understanding of how this could transform space access, if it can be built at all, this is your essential shortcut.
Okay, so to start, let's define exactly what we're talking about. The modern tensile design of the space elevator.
Right. It's an Earth-based system with 4 essential components, and they all have to work in perfect concert. First, you need a cable, a tether or ribbon that's anchored somewhere near the equator.
And that's crucial, the equator part. You need that maximum rotational assist from the Earth.
Absolutely. Then the second critical component is that this cable can't just stop at the edge of space.
Right, it has to keep going way, way out.
It has to extend far beyond what we call geostationary orbit, or GEO. That's at an altitude of 35,786 kilometers.
A lofty altitude.
Very. And third, at that upper end, far out in space, you need a substantial mass, the counterweight.
And that counterweight is really the linchpin of the whole thing, isn't it? It's not just a weight sitting there.
Not at all. It's the rotational energy of that weight that holds the entire system up. It's the anchor that keeps the cable taut against Earth's gravity.
So it's whipping around with the Earth's rotation, and that inertia generates this massive tension.
Precisely. And then fourth, you need the mechanical transport. The climbers, sometimes called crawlers, that move cargo and people up and down that stationary cable.
And the core benefit, the thing that drives all the research and all the investment.
It's transformative. You get direct, high-volume travel between the surface and orbit without needing massive, repetitive, and hugely expensive chemical rocket launches. It makes space access feel less like this heroic undertaking and more like, well, logistics.
Like running a freight train to the stars. Now, this might sound like a very new concept, something driven by 21st century material science, but the audacious dream of connecting Earth and space with a stationary structure actually began well over a century ago.
Way back in Tsarist Russia, actually.
Yeah. We have to start with Konstantin Tsiolkovsky in 1895. He's known as the father of rocketry, and in his collection Dreams of Earth and Sky, he envisioned what he called a massive Sky ladder.
A sky ladder to overcome gravity. But here's where the history gets really interesting and often a little confused. Tsiolkovsky's original concept was not the modern tensile design we're talking about today.
It was a tower, correct, a compression structure.
Exactly. He envisioned a colossal aerial mast, a tower built from the ground up, held in place by its own structural rigidity, like a skyscraper, but reaching 100 kilometers or more.
Which was, ultimately deemed impossible.
Yeah, completely impossible. The materials at the time and even now just couldn't do it. To hold up the mass of the tower above it, the base would need to be impossibly wide. It would just collapse under its own colossal weight long before it got anywhere near orbit.
So the idea of a fixed structure was sound, but the method was impossible until someone, flipped the whole concept on its head.
And that's exactly what happened independently in 1960. A Russian scientist named Yuri Artsutinov developed what he called a cosmic railway.
His idea was to build down, not up.
Precisely. Launch a satellite into geostationary orbit first, and then deploy a cable downwards, using the centrifugal force of a counterweight above to keep the cable taut. This tensile design, held up by tension from space, is the foundational design we use today.
And the idea eventually made its way to the West, and that's when it got some critical design refinements in the U.S.
Right, that momentum started pretty quickly. In 1966, John O. Isaacs and his team introduced the skyhook concept. They really hammered home the importance of extending the cable downward from a GEO satellite.
But the really rigorous engineering analysis, the stuff we rely on today, was solidified about a decade later with Jerome Pearson.
Pearson is incredibly important. He started researching this seriously in 1975. He was an engineer for NASA and the Air Force Research Lab, and he developed the detailed design for the orbital tower.
And his big contribution was figuring out the actual geometry of the cable itself, which is a highly complex calculation.
It is. He calculated that because of the varying forces of gravity and centrifugal pull, the cable would need to be thickest right at GEO altitude.
Where the tension is the greatest.
Absolutely, where those opposing forces are at their maximum. And then it would have to taper dramatically toward both ends, toward the surface and toward the counterweight. It was a crucial detail for minimizing the total mass of the system.
And his calculations for the counterweight really showed just how massive this thing would have to be.
They really did. He proposed a massive counterweight, potentially extending the cable structure to an incredible 144,000 kilometers.
89,000 miles. That's nearly halfway to the moon.
It's an immense distance. And he also started analyzing all the external forces, like the moon's gravity trying to pull on the structure and things like wind and lightning near the base. He treated it like a real dynamic system.
It feels like Pearson made the leap from a theoretical curiosity to a detailed engineering problem.
He did, and that's where the concept truly entered the cultural sphere. Pearson's findings directly influenced Arthur C. Clarke.
For his 1979 novel, The Fountains of Paradise.
Exactly. That novel, and another one, Charles Sheffield's The Web Between the Worlds, introduced the space elevator to a massive global audience. It went from obscure engineering papers to this plausible, aspirational technology.
And that spurred renewed interest, leading to a NASA conference in 1999 on this very topic.
Right, but that initial 2000 NASA report basically concluded it couldn't be built for at least 50 years. The materials were the main problem.
But then the assessment shifted pretty dramatically in the early 21st century.
It did, because of the tantalizing promise of nanomaterials, specifically carbon nanotubes or CNTs.
And Dr. B.C. Edwards became a key proponent around that time.
He did. He proposed a detailed design using a 100,000-kilometer-long paper-thin ribbon made of a carbon nanotube composite.
His work was incredibly comprehensive, detailing everything from the climbers to the anchor systems, including this revolutionary idea of a mobile oceanic anchor.
Yeah, that was a huge step forward for safety, maneuvering the anchor to avoid things like hurricanes or lightning strikes. His work really helped transition the elevator from a distant future concept into a serious near-future design goal.
Which led to some high-profile commitments. Japan's Obayashi Corporation announced they aimed to build one by 2050. We've seen miniature elevator experiments on CubeSats. Even Google X took a serious run at it.
Right. And the current position from the International Academy of Astronautics is one of qualified optimism. They think it's feasible if material science can deliver that necessary fiber. That remains the single critical hurdle.
Okay, so let's unpack this. Before we even get to that material hurdle, we need to understand the underlying physics. The whole thing sounds deceptively simple. A cable and a weight. But the dynamics holding it all together are where it gets really interesting. How does a massive cable stay upright?
The stability of the space elevator relies on a really elegant and precise balance between two fundamental opposing forces.
You've got gravity, which is pretty intuitive. It's pulling everything down toward Earth's center.
Right. And that force gets weaker the further you go out. The counteracting force is the upward centrifugal pseudoforce, or, what's often just described as inertia from the system's rotation.
So everything, the cable, the counterweight, the climbers, is rotating with the Earth.
At the same angular velocity, so they all possess immense inertia. The counterweight, way out there, is constantly trying to fly outward in a straight line, but the cable holds it back.
Creating that immense tension.
Exactly. And that upward centrifugal force is dramatically stronger the further you get from Earth's center.
So you have downward gravity, which dominates close to the surface, and upward inertia, which dominates way out in space. They have to find a sweet spot.
And that sweet spot is the essential pivot point for the whole system. The geosynchronous equatorial orbit, GEO, at 35,786 kilometers up.
That's the point where the two forces are perfectly balanced.
Perfectly balanced. The downward pull of gravity and the upward centrifugal force are equal. Any object fixed to the cable at that exact point puts zero net weight or stress on the cable.
And it's what happens above and below GEO that makes the whole system work.
That's the structural genius of it. Above GEO, the upward centrifugal force is stronger than the now diminished gravity. So the counterweight and everything up there is pulling upward on the cable, generating that immense tension that keeps the whole thing vertical.
Like a giant guitar string pulled tight from space.
A perfect analogy. And below GEO, gravity is stronger, pulling objects downward, but that force is completely opposed by the tension from above.
Which leads to this really interesting concept of the apparent gravitational field. Since you're connected to the cable, you're not in free fall. You're feeling the net force of these two opposites.
That's a perfect way to put it. The apparent gravitational field is just the net force you feel. It's basically the downward gravity minus the upward centrifugal force. And it tells you which way you'd accelerate if you let go of the cable.
So if I'm a payload climber and I'm ascending below GEO?
Below GEO, gravity is stronger, so the apparent gravity pulls you downward toward the anchor point. If you let go, you'd initially accelerate down the cable.
But you'd also start to deflect eastward, right?
Yes, because you're rotating with the Earth. You'd seek a lower, slower orbit, which appears as an eastward deflection.
And then once you cross that GEO pivot point, everything flips.
Precisely. Above GEO, the centrifugal force is stronger. The apparent gravity now pulls you upward toward the counterweight. If you let go of the cable up there, you'd accelerate upward along the cable and then deflect westward as you entered a higher orbit.
So it becomes a kind of mechanical slingshot. You can launch payloads into deep space just by letting them go at the right height.
Which is one of its most powerful applications. No rocket propulsion needed after the ascent.
Okay, but if the Earth is rotating and you have these massive climbers, maybe 20 tons of cargo, moving up and down, how does that affect the rotation of the planet itself?
It does. This is the challenge of angular momentum transfer, which is driven by the Coriolis effect.
So as a climber goes up, it's moving from a point of lower horizontal speed near the surface to much higher horizontal speed near GEO. It has to gain that speed from somewhere.
And it draws that speed directly from the Earth elevator system. The climber essentially drags westward on the cable as it climbs. And this force, this Coriolis force, translates to an infinitesimal slowdown, a tiny decrease in Earth's rotation speed.
An infinitesimal slowdown of the planet every time a cargo ship goes up. So conversely, descending payloads must give that momentum back.
Correct. As they descend, they shed that horizontal speed, and the momentum is absorbed by the cable and transferred back to the Earth, slightly speeding it up.
So if you have symmetrical traffic, the net effect is zero.
Over time, yes. But what if the traffic isn't symmetrical? What if you're constantly lifting thousands of tons to build space stations and nothing is coming down?
Then the cable would start to lean.
It would lean slightly westward, yes, because of the continuous drag from the ascenders pulling it out of perfect vertical alignment. But here's the saving grace of the design.
The counterweight pulls it back.
The immense centrifugal force from that massive counterweight is constantly trying to pull the entire system back to the vertical orientation, just like a giant pendulum. So the cable is never perfectly still. It's always oscillating, always correcting itself.
Which means you have to manage those oscillations very carefully.
You absolutely do. You have to pace the climbers to keep that pendulum-like motion under control. Uncontrolled oscillation could drastically increase the stress on the cable, and you can imagine what would happen then.
A catastrophic failure. The physics are stunningly elegant, but they also show how close to the limit the system operates. And it all relies entirely on one thing.
A cable that can withstand these forces and not just snap.
And that is the absolute single biggest hurdle. It has been since the concept was first refined. The number one challenge is material science.
Specifically, the need for an extremely high strength-to-weight ratio. We call it specific strength.
And why is that ratio, and not just pure strength, the deciding factor?
Because the material has to be strong enough to hold up its own weight all the way to GEO, 35,786 kilometers up. If a material is incredibly strong but also incredibly dense, like a thick steel rod, it will just break under its own dead weight long before it even gets out of the atmosphere.
We need something that's both light and ridiculously strong.
And at the same time, yeah. And if you look at conventional materials, they're just shockingly inadequate.
What are the breaking lengths we're dealing with today?
Well, breaking length is the maximum length of a material that can support its own weight. For things like titanium, steel, aluminum alloys, you're talking 20 to 30 kilometers. That's it.
Modern fibers like Kevlar are better.
A bit better, yeah, 100 to 400 kilometers. But the minimum theoretical breaking length you need for an untapered cable just to reach GEO without breaking,
I have a feeling this number is going to be big.
it's immense. The requirement is 4,960 kilometers.
4,960. Compared to Kevlar's max of 400, we're not even in the same ballpark.
Not even close. We're short by a factor of 12, even with our best current materials. And this is where the concept of the taper ratio becomes absolutely critical.
Because we don't have that super material, so we have to use geometry to make up for it.
Exactly. As Pearson established, the cable can't be a uniform thickness. It has to be thickest at GEO, where the tension is greatest, and then taper dramatically toward the ends. The taper ratio is just the ratio of the area at GEO compared to the area at the anchor.
So walk us through the math here, because the numbers are just, well, they're literally astronomical.
They are. If the specific strength is too low, the taper ratio becomes exponentially large. So let's take steel. The required taper ratio for steel is 1.6 times 10 to the power of 33.
A non-Ilian. That's a number that doesn't even feel real. You'd need a cross-section at GEO that's 1.69 million times thicker than at the surface.
It's scientifically unfeasible. Even using Kevlar, the ratio is still 2.5 times 10 to the 8, or 250 million. The total mass of the material is just impossible.
So doesn't that make the entire concept dead on arrival until that fiber exists? Are we just talking about science fiction dressed up as engineering?
That is the core debate. And to make it feasible, engineering studies calculate we need a specific strength approaching 48 megapascals per kilogram per cubic meter.
Which is a pretty abstract unit for most of us.
It is. So the International Space Elevator Consortium created a more accessible unit, the Yuri, named after Artsudanov.
A Yuri. So what do we need in Yuri strength?
A functional Earth elevator requires a tether of 30 to 80 megayuri, which corresponds to a breaking length of about 3,100 to 8,200 kilometers.
Okay, so that's getting into the right territory.
It's getting closer. And this is why, after conventional materials failed, all hope pivoted to nanotechnology, specifically carbon nanotubes.
Because carbon is super light, and the theoretical bond strength of the atoms is immense.
Exactly. CNTs seemed like the perfect solution. Edwards' design back in the early 2000s assumed a material with a specific strength of 77 megapascals per cubic meter, a number only CNTs seemed theoretically capable of meeting.
But that dream has faced a massive reality check.
A huge one, moving from theoretical possibility to manufacturing impossibility. The problem is that while tiny lab strands show immense strength, that integrity just plummets when you scale it up.
All about atomic perfection, right?
It comes down to that. For a CNT to reach its full strength, its hexagonal lattice structure has to be absolutely flawless. Even one single atom out of place creates a defect that drastically decreases its tensile strength.
And the practical manufacturing challenge is still completely unsolved.
Critically so. This is why Google X shelved their project. They realized that no one has ever manufactured a perfectly formed, structurally sound carbon nanotube strand longer than 1 meter.
1 meter. And we need a 100,000-kilometer cable.
It's a huge gap. But the quest for the perfect fiber hasn't ended. Researchers are now focusing on other nanomaterials.
What are the new contenders?
Things like boron nitride nanotubes, which are similar but more stable, diamond nanothreads, which were first synthesized in 2014, and the latest focus of the IAA studies is macroscale single crystal graphene.
So the consensus seems to be that we just have to wait for a revolution in material science on Earth before we can even begin talking about construction.
That's the hard truth. The physics are sound, the engineering concepts are mature, but it all depends on that flawless, ultra-strong fiber existing first.
Okay, so let's assume for a minute that material science delivers. We get a ribbon of 80 megauri strength. Let's pivot to the infrastructure you'd need to actually deploy and operate this thing, starting with the base station.
Right. Modern proposals favor highly sophisticated mobile base stations, usually large ocean-going vessels or platforms anchored near the equator.
And what's the advantage of having it be mobile? A fixed structure on land seems simpler.
Mobility provides a couple of crucial advantages for safety and operation. First, it allows the base to maneuver to avoid atmospheric hazards like hurricanes or severe storms.
Which would put huge lateral stress on the tether.
Catastrophic stress. And second, and this is maybe the most critical part for long-term survival, mobility allows the anchor to dodge trackable space debris.
Right, because the tether is a massive navigational hazard.
It is. So the mobile anchor can slightly shift the cable's position over time to avoid predicted collisions. It's essential to prevent a catastrophic cut. And third, you're in international waters, which simplifies the immense geopolitical challenge of it all.
Okay, so the cable is anchored. Now, the transport vehicles, the climbers, how do they actually move up a 100,000-kilometer ribbon?
For the thin, ribbon-like cables, most designs use friction rollers to grip the ribbon. They're basically just electric-powered machines climbing a vertical road.
And throughput is critical for the economic case. How fast are we talking? This isn't a quick trip.
No, it is not. The speed is limited by power, the cable's thermal tolerance, and those Coriolis forces. Even at a very fast rate, say 300 kilometers per hour.
Like a high-speed train.
Exactly. The transit time to GEO would still take about 5 full days.
5 days of straight vertical ascent. Which brings us to power. How do you power a vehicle for that long over that distance?
That's one of the biggest engineering challenges after the cable itself. The currently favored method is laser power beaming.
Which sounds like pure science fiction.
But it's solid, cutting-edge engineering. You have megawatt-powered lasers on the ground, shining a highly focused energy beam up to a photovoltaic array on the climber. The array converts that light into electricity to run the motors.
What are the hurdles there? Beaming megawatt power through 35,000 kilometers of atmosphere.
Several huge ones. First, atmospheric absorption and scattering. Clouds, humidity, turbulence, they all sap energy from the beam. Second, you need incredibly precise targeting and adaptive optics to keep that beam focused on a tiny moving target tens of thousands of kilometers away.
And the energy requirement must be staggering. Are you powering a small city for one launch?
For a large 20-ton climber, yes, the power input could be in the range of 10 to 20 gigawatts. The output of a dozen large nuclear power plants focused purely into that beam.
Wow, okay, let's talk safety again. A 5-day transit means a lot of exposure to the Van Allen radiation belts.
That is a severe and often understated concern for passenger travel. That prolonged exposure means you'd need significant shielding for any humans on board.
And that shielding adds mass. Does that destroy the economic advantage?
That's the perfect critical question. For human passengers, yes, the added mass of shielding absolutely decreases the payload capacity and drives up the cost per kilogram. It might even push it back towards rocket pricing for human transit. This is why initial concepts are all about cargo.
Right. And finally, the counterweight. The big balancing act. What are the options?
3 main options. You could use a captured near-Earth asteroid. You could build a large, purpose-built space dock or station out past GEO. Or, the simplest option, you just extend the cable itself further upward and attach mass to the end.
And extending the cable gives you that huge bonus application, deep space launch.
It's the ultimate feature. Extending the cable far beyond GEO turns the upper segment into a momentum launch system. A released payload instantly possesses tremendous horizontal speed.
How far can that reach?
If you release a payload from 100,000 kilometers up, it has enough speed to reach the asteroid belt. If you extend it to Pearson's proposed 144,000 kilometers, the velocity upon release is a staggering 10.93 kilometers per second.
That's enough to send probes to Jupiter.
At least Jupiter, yeah. It completely changes the economics of interstellar exploration.
So let's talk dollars and cents. Because the true driver behind investing trillions into a material that doesn't exist is the economic case.
And the disparity is staggering. As of 2022, conventional rockets cost about $12,125 per kilogram to get to GEO.
Which is why space is so prohibitively expensive.
Exactly. Space elevator proponents envision payload prices starting as low as, well, $220 per kilogram, maybe $500 per kilogram to GEO and beyond.
Even if we're conservative and say it's $2,000 a kilogram, that's still a 95% reduction in cost. That doesn't just change space access. It creates entirely new industries that are impossible today.
And that potential for control is why the geopolitical incentive is so high. One proponent said the first country to deploy a space elevator would have a 95% cost advantage and could essentially control all future space activities.
But those low cost per kilogram figures, they have to be tempered, right? Trillions to build, the insurance, the operational risk.
They have to be. Those figures often don't include the massive capital expenditure. Realistically, you're probably looking closer to $1,000 or $2,000 per kilogram initially. But even then, the economic advantage is still decisive.
Okay, so how do you even build it? You can't just launch a 100,000-kilometer cable on a rocket.
The key is the spool concept and bootstrapping. You launch a relatively small seed cable on a large spool into GEO using conventional rockets.
And then you unspool it.
Exactly. You pay it out downward toward Earth, while at the same time you pay out a balancing mass upward away from Earth. This keeps the whole system's center of mass right at GEO.
So the initial cable is just a scaffold.
It is. One plan suggests a seed cable that could only support the very first tiny 619-kilogram climber. Then subsequent climbers carry up more material to attach and thicken the ribbon over time.
So the first elevator builds the second, and so on.
Yes, you'd bootstrap your way up to full capacity.
But if the material requirements for Earth are so extreme, are there places in the solar system where this is actually easier to build?
Yes, significantly so. And this is a critical point. The material requirements are much, much lower on smaller celestial bodies.
Let's start with Mars.
Mars is highly favorable. Its gravity is only 38% of Earth's, and it rotates at about the same rate, so the elevator could be much shorter. And crucially,
The materials already exist.
current available materials like Kevlar are already strong enough and light enough to construct a Martian space elevator.
We don't need carbon nanotubes for Mars. The technology is basically ready to go.
From a materials science perspective, yes. Building it would be complicated by the moon Phobos, but the material isn't the barrier.
What about our moon? It's tidally locked, so the centrifugal force method wouldn't work.
That's correct. But you could still build one using differential gravity forces, anchoring it through the Earth-Moon L1 or L2 Lagrangian points.
And again, the material requirements.
Low enough to use existing engineering materials?
So the core takeaway is that the space elevator isn't a single impossible project. It's a spectrum. Earth is at the very hardest end, waiting for a materials miracle. But Mars and the Moon are ready for construction right now.
And that just reinforces that the challenge isn't orbital mechanics, it's manufacturing.
So this deep dive has shown us the breathtaking scale of the space elevator concept. We've covered the elegant physics of that GEO balance point, the angular momentum transfer, that slight westward drag on the planet.
And the transformative economic impact. Shifting space access costs from over $12,000 a kilogram down to maybe a few hundred.
But the entire enterprise hinges on solving that single monumental challenge, material science. We quantify the problem with the taper ratio and the required strength in Megaeurus.
And the International Academy of Astronautics concluded that, while it seems feasible, the only thing holding us back is the ability to reliably manufacture flawless nanostructured materials at kilometer-scale lengths.
We are waiting for a breakthrough, not in rocket science, but in materials engineering and carbon processing, right here on Earth.
Which raises a powerful question for you, the listener, to think about. We've established that the material required is a flawless fiber, maybe single crystal graphene or a diamond nanothread, 100 times stronger than steel and incredibly light.
So if researchers successfully scale up production of this material, a manufacturing challenge right here on Earth,
what global industry outside of space travel do you think would be the first to be utterly transformed by a material that is effectively unbreakable? Think construction, automotive safety, power transmission, or something else entirely. That's the technology we need to watch, because when that terrestrial barrier falls, the skyhook will be next.
Welcome back to the Deep Dive. Today, we are taking on a true heavyweight of human history.
We really are.
We're discussing an invention that historians, they frequently rank it as one of the most influential events of the entire second millennium.
An engine of change.
Yes, an engine of change so profound it literally reset the operating system of Western civilization. We are diving deep into Johannes Gutenberg's movable type printing press.
That ranking is, I think, absolutely justified, and frankly, it might even be an understatement.
Really?
Oh, yeah. We are talking about the foundation of mass communication itself. If you think about every revolution that followed, religious, scientific, political, they all required the ability to share complex, identical information rapidly across huge distances.
So our mission today is to unpack not just the genius of the technology itself back in the 15th century, but the true magnitude of the transformation that started in Mainz around 1440.
Exactly.
Let's start with the sheer mechanics, because understanding the simplicity of the machine is kind of key to understanding the profundity of what it could do. It really is.
At its core, the printing press is a mechanical device. It's designed to apply pressure to an inked surface that's resting on something like paper or cloth, and that's how it transfers the ink.
Right, and the earlier printing methods, like woodblocks, they required the printer to brush or rub the back of the paper by hand to get that ink transfer. It was a slow, painstaking process.
The brilliance of Gutenberg, then, wasn't inventing the idea of printing.
No, not at all. It was inventing the mechanical system that made printing fast and accurate enough to matter on a global scale.
And the contrast in speed, that's where the story really is. It's the quantifiable leap that tells you everything.
It's staggering. Before Gutenberg, texts were primarily hand-copied by scribes. You might get just a few pages done in a day. If you were doing manual woodblock printing, maybe on a really good day, you'd hit 40 pages.
40 pages, okay. Versus, what could a single Gutenberg-style press actually manage?
Well, once it was up and running with a skilled two-person crew, a single setup could produce up to 3,600 pages per workday.
3,600. 3,600. And that's based on, an average working day and all the human movements required. That is productivity that leaps from just artisanal labor straight into something that looks a lot like industrial output, almost overnight.
And that shift is what broke the monopoly of the literate elite. So our goal for this deep dive is to see how this invention synthesized existing knowledge, what specific technical bits Gutenberg perfected that others had missed,
and how that perfection acted as a fundamental engine for societal, cultural, and political transformation across Europe and eventually the entire globe.
So prepare for a deep dive that looks at physics, finance, and philosophy.
The first question we have to tackle is context. I mean, if Gutenberg invented the system in 1440, why did it happen then, and why did it happen there in a relatively small city like Mainz?
It was a perfect storm, really.
It was a perfect storm of social and economic pressures. The climate was just incredibly favorable.
We hear a lot about the Renaissance, humanism, all that, but the economic side of things is often overlooked. Let's talk about the economic context. The rise of the merchant class, emerging capitalism.
This is so crucial. Late medieval society was experiencing really rapid economic development. You had this burgeoning merchant class accumulating wealth, and with that wealth came an aspiration for education, for status, things that were previously just for the nobility or the clergy.
Right.
So this emerging capitalist spirit, it fostered entrepreneurial thinking. People were actively looking for better, faster ways to produce goods, and that included intellectual goods. Gutenberg himself was operating very much as an entrepreneur. He was looking for a financial advantage.
And that search for an advantage introduces a really important complication right at the start. Risk and funding. He didn't do this alone, did he?
Not at all. The entire venture was extremely capital intensive. You needed specialized tools, you needed metal, you needed years of secret experimentation.
So you needed backers.
You needed financial backing. Gutenberg famously entered into agreements with financiers, most notably a man named Johann Fust, who was a wealthy goldsmith from Mainz. Fust gave him a substantial loan specifically to fund the experimental phase and build all the necessary tools.
So the economic climate didn't just create the demand, it provided the venture capital for a risky long-term project.
Precisely. It was a classic supply-side opportunity meeting a massive demand-side problem.
And the cultural context was just as important.
Just as vital. There was a sharp rise in medieval learning and literacy, especially among that educated, aspiring middle class, your lawyers, doctors, merchants. They needed legal texts, practical guides, devotional materials, even popular literature. The market was massive, and it was desperate.
And hand copying just couldn't keep up.
Not even close. The system was crying out for a scalable solution.
And it's important to acknowledge, as our sources point out, that Gutenberg was a brilliant synthesizer. He wasn't creating everything from scratch.
That's right. He successfully combined what you could call far-flung strands of existing technology into one complete commercially viable system.
Which brings us to the foundational tech, the press itself. It relied on a machine that had been around for over 1,000 years.
The screw press.
Yeah.
This device, it uses a threaded mechanism to apply direct, concentrated pressure. It was ancient. The Romans introduced it in the 1st century AD.
And it was everywhere because it was essential for daily life.
Yes. It was standard agricultural technology. It was used all across Europe for pressing grapes for wine, olives for oil. So the technology was robust. It was well understood. It was everywhere. Gutenberg didn't need to invent the machine that delivered the pressure.
He just had to adapt it.
He just adapted it.
But adapting a grape press to print tiny, precise letters seems like a massive leap. What was the core mechanical challenge he had to solve there?
Well, the difference is in the type of pressure you need. For wine or oil, you need a slow, sustained, crushing force. For printing, you need a powerful, perfectly even and sudden pressure, what printers often called the kiss. It presses the paper against the type and then immediately releases.
If it's too slow, the ink would smear.
It squishes and smears. If it's uneven, some areas just won't print. So Gutenberg adapted the construction, probably inspired by paper presses, to make sure the pressure was distributed perfectly and applied with the speed and elasticity you needed for a clean transfer.
That distinction-crushing force versus the kiss, that explains the mechanical innovation. Okay, let's move to the most crucial component, the movable type itself. The concept of reusable individual characters had been around for centuries, globally speaking.
Absolutely. We have to give credit where it's due here. The first movable type was actually invented by a Chinese engineer, Bi Sheng, way back in the 11th century, and he used baked clay.
And then in Korea?
In Korea, we see the oldest surviving book printed using metal movable type, the Jikji, and that dates back to 1377.
So the idea was there, the material was there. Why didn't those earlier innovations trigger a global knowledge revolution? Why did Europe have to wait another 70 years?
This is a really critical point. There are two main reasons. First, the Chinese writing system, being logographic, it requires thousands of different characters. Bi Sheng's invention was brilliant, but it was just highly inefficient to manage tens of thousands of individual pieces of type.
Okay, and the second reason?
Well, regarding the Korean metal type, while the concept was sound, the production methods, imprinting or punching, they just lacked the refinement needed for mass application. And critically, in many of these earlier systems, the printing was often still done manually by rubbing the back of the paper.
Which keeps you in that low volume, 40 pages a day range.
Exactly. Gutenberg's genius was integrating and perfecting all the components needed for true mechanical efficiency, from creating the type to applying the pressure.
And two other massive technological factors were already in place in Europe that made this possible: the book format and the raw material.
Right. The book format had been standardized for almost 1,000 years. The codex, folded pages bound at the spine. It replaced the ancient scroll way back around 500 AD.
And it was just better.
Incredibly superior, easier to read, easier to store, and crucially, it allowed printing on both sides of the sheet, the recto and verso. That saved a massive amount of materials. The format was ready for mass production.
The material that the press would crush against, paper. Paper was indispensable.
Paper was the economic multiplier. The success of medieval paper makers and mechanizing paper manufacture using water-powered paper mills was absolutely key.
And crucially, it reduced the price.
Drastically. Once it was mechanized, paper fell to 1/6 the price of expensive parchment, which is made from animal skin. Without cheap, abundant paper, the idea of printing 20 million volumes by 1500 would have been economically impossible.
So by 1440, you have the funding, the demand, the mechanical blueprint of the screw press, the convenient codex format, and cheap paper. All Gutenberg had to do was fill that crucial technical gap.
And that's where his background as a goldsmith comes in. This is where we see his real genius. He didn't just see printing as one job. He saw it as an industrialized process.
Right. He separated typesetting and printing into two separate optimized steps.
He treated the production of text like the minting of coins. It demanded total precision.
His specific training was everything, wasn't it? If he had been a carpenter, he could have built the press, but he wouldn't have had the metallurgy skills to solve the type problem.
Exactly. The primary innovation wasn't the press structure, it was the type and the rapid, standardized way he made it. Gutenberg was the first to create durable, high-quality type from a very specific alloy.
It wasn't just lead. That would have been too soft, it would deform under pressure.
No, it was a precise tripartite alloy. Lead, tin, and antimony. And this combination was so perfect for printing that, remarkably, the alloy is still used today for some applications.
Why those three metals? What did each one do?
Well, lead provided the bulk and the low melting temperature. Tin was added to lower the melting point even more and improve the flow of the liquid metal, making sure it filled every nook and cranny of the mold. But the really innovative part was antimony.
Antimony.
Antimony is one of the few elements that, when it solidifies, actually expands slightly.
So instead of shrinking away from the edges of the mold, which would ruin the precision.
It pushed outward against the mold walls, and that ensured the type came out with perfectly sharp edges and corners, which is non-negotiable if you want crisp, clear letters.
The alloy solved the durability problem, but you still need to make hundreds, thousands of identical pieces of type quickly.
And that's where his most ingenious invention comes in. The special hand mold, or the matrix. This adjustable two-part metallic device was the true secret to the revolution. It allowed for the quick, non-destructive mass production of uniform metal letters.
We have to walk through the mechanics of that. What did the compositor do?
Okay, so the compositor would engrave a letter into the end of a steel punch. This punch was then hammered into a softer copper bar, creating a perfect reverse impression. That's the matrix, the master template.
And that matrix was placed in the bottom of the hand mold.
Exactly. Then the molten lead-tin antimony alloy was poured into the top. Once it cooled, which was very quick, the compositor could rapidly release a brand new, perfect piece of type.
And the mold itself was adjustable.
Crucially, yes. It could be adjusted for a wide W versus a narrow I, while making sure the most important element, the height, was always exactly identical. Without that, the pages would be uneven, and the press would just destroy the type.
So the alloy solved durability, and the hand mold solved scalability and precision.
Correct. And you also have to consider the incredible practical advantage he had working with the Latin alphabet.
Right, compared to the thousands of characters in Chinese writing.
It was an enormous advantage. You only needed a theoretical minimum of around 24 different letters. Now, in practice, his full typecase had about 290 separate compartments.
Why so many?
Well, for ligatures, 2 letters joined as one, special characters, different font sizes, punctuation, everything you needed to make the printed text look as sophisticated as a handwritten script. But managing 290 boxes was infinitely easier than managing thousands.
And finally, the ink. You're using a powerful mechanical press with metal type, so you can't use the standard medieval ink.
No, that was water-based. It would just soak the paper and smudge immediately. So Gutenberg, through a lot of experimentation, introduced an entirely new oil-based ink formula.
And that was a critical solution.
It was. It was thicker, stickier, more durable. It adhered perfectly to the metal type and transferred cleanly onto the damp paper without soaking through. It was essential for that high-quality, crisp impression.
And we have to talk about the aesthetic quality of his early works. He wasn't just going for speed. He was aiming for beauty.
Absolutely. The 42-line Bible, printed between 1450 and 1455, is his masterpiece. It was printed on both paper and incredibly expensive vellum. He used a dense black ink, a rich typeface, and he even left spaces for illuminators to hand-add colored initials. He was trying to replicate and surpass the beauty of the manuscript tradition.
And he was already pushing the boundaries beyond just black text, even that early.
Definitely. The 42-line Bible had a trial of color printing for a few headings, but the main Psalter of 1457, which was produced by his successors, took it even further. It featured these elaborate red and blue printed initials, which required an incredibly complex double printing process to get the registration perfect. So you can see they were rapidly exploring color printing, making the press an engine for visual, not just textual, communication.
So now that we understand the breakthroughs, the type, the mold, the inklet step inside a 15th century print shop, what would a classical Gutenberg-style wooden press look like?
Well, they were surprisingly large, sturdy machines. They were typically, 5 to 7 feet long, about 3 feet wide and 7 feet tall. Big, heavy wooden frames. They had to be robust enough to withstand the incredible torque needed for that kiss of pressure.
And the workflow was an early example of specialization. It started with a compositor.
That's right. First step was typesetting. The compositor would stand at a case holding all the little metal letters. They'd arrange them backward and upside down into a handheld composing stick, line by line.
Which sounds incredibly difficult.
It was. These lines were then transferred into wooden frames called galleys. Once a full sheet's worth of text was composed, those galleys were locked into a big frame called a form, and that was placed on the flat stone bed of the press, ready for inking.
And that process demanded high literacy, immense patience, and absolute precision.
It did, and it led to the specialized role of the corrector. The corrector would proofread a printed sheet, the galley proof, before the full run began. Because composing backward was so mentally taxing, corrections were constant and critical.
Once the type was locked in, how is the ink applied?
It was a very skilled process, using two tools known as balls or pads. These were mounted on wooden handles and made of dogskin leather.
Dogskin? Why?
Specifically because it's non-porous, so it wouldn't absorb the oily ink. They were stuffed with sheep's wool to give them a springy feel. The pressman would dab these balls on the ink slab and then systematically beat the ink evenly across the type.
So it was a rhythmic, practiced motion?
Absolutely. And while the inker did that, the paper preparation was also happening. The paper was deliberately dampened.
Why damp the paper? Wouldn't that lead to tearing?
It was a delicate balance. It needed to be just damp enough to relax the fibers and let the type bite into the paper, ensuring a crisp impression without tearing.
And that damp sheet was secured onto a frame.
Onto a hinged frame called the timpan. And on top of that, you had another frame, the frisket.
Wait, what did the frisket do?
The frisket was very clever. It had holes cut out that corresponded exactly with the pages of type. So when it was folded down, it acted as a mask, preventing ink from getting on the margins of the paper.
So it kept everything clean?
Yes. They folded down together, and often a wool blanket was placed between them to form an elastic pad. This helped cushion the tremendous force of the press.
So once everything is aligned, the bed of the press has to be moved under the platen, the heavy plate that provides the pressure.
Right. And that was done by turning a small crank handle called the rounce. This would roll the heavy form into the exact position under the platen.
And then the final act, the impression, achieved by turning that long handle.
That long handle was known as the bar or the devil's tail. The pressman would grab the bar and, using immense leverage, turn the central screw that transmitted that final powerful pressure down through the platen.
It sounds like a continuous, physically punishing cycle.
It was, and that's why the labor was split. You had a two-man team. The inker, applying the ink, and the puller, who pulled the bar. Together, they could achieve 14,000 hand movements in a working day.
You can just imagine the scene. The clanking, the snap of the bar, the smell of oil ink and damp paper, the beating heart of the printing revolution.
And the genius of the system was that it was immediately reproducible. It spread like wildfire because its demand was so desperate.
Let's talk about that speed. It started in Mainz, but how quickly did it become a European phenomenon?
And the diffusion rate is truly remarkable. Starting from that single shop, printing spread to over 200 cities in a dozen European countries within just a few decades. By 1480, printers were active in 110 different places.
Wow.
The printed book was basically in universal use in Europe from that point on. The genie was out of the bottle.
And the sheer quantitative output is just mind-boggling.
By the year 1500, just 55 years after the first Bible presses in Western Europe had produced more than 20 million volumes.
20 million.
And it only accelerated. In the 16th century, output rose tenfold to an estimated 150 to 200 million copies.
And to give that some context, we have the anecdote about Erasmus. At least 750,000 copies of his work were sold during his lifetime alone. That's an intellectual celebrity phenomenon on a scale nobody had ever seen.
And this scale quickly led to a profound cultural and political earthquake. The most famous example, of course, is the Reformation.
The press was absolutely critical to its success.
Some would argue indispensable. The press turned a theological argument into a media war, and it caught the established authorities completely off guard.
How so?
The numbers are staggering. Between 1518 and 1524, book publication in Germany skyrocketed sevenfold. Martin Luther used the press brilliantly. He wrote short, sharp tracts in the vernacular that could be cheaply and rapidly distributed. Between 1518 and 1520 alone, 300,000 printed copies of his tracts were distributed.
That's faster and wider than any message had ever moved in history.
It was a shock of velocity. The Catholic Church's traditional response mechanisms, condemnation, excommunication, were designed for an age of slow, hand-copied texts. By the time Rome issued a response, Luther's next tract was already on the streets.
The establishment just couldn't keep up.
They couldn't contain it. And this unrestricted circulation of ideas is why the machine lent its name to the medium itself. We still call it the press.
And that medium became associated with the fight for political freedom, the English Civil War, the American and French revolutions.
All leveraged pamphlets and bulletins, but that power immediately led to issues of censorship and the endless battle for freedom of the press. The authorities realized very quickly that this was a weapon that needed to be controlled.
Beyond politics, this was the true democratization of knowledge in action.
The monopoly of the literate elite, the clergy, court officials, it was fundamentally broken. Knowledge was suddenly accessible and cheaper, which directly bolstered the emerging middle class. It created a self-reinforcing cycle. Cheaper books led to more literacy, which created demand for more books.
The press also solved a crucial problem that hand copying never could: consistency.
The standardization of knowledge. This is maybe the most profound intellectual consequence, because the process ensured the exact same information was on the exact same pages. Scholars could finally refer to an identical text.
And that led to things we take for granted now.
Exactly. Page numbering, tables of contents, indices, these things became common.
How did something as simple as page numbering change things in a field like law or medicine?
It created certainty. A doctor could now direct a colleague to Plate 3, Figure 7, page 112, knowing they were looking at the precise same image. It allowed for exact citing of references, which dramatically increased the reliability of knowledge systems.
And it created the modern concept of authorship.
It made authorship meaningful and profitable for the first time. Before the press, the author's name was often lost. But now it became critical to know exactly who had said or written what.
And this standardization didn't just affect organization, it affected language itself. Latin was still the lingua franca for scholarly work.
Latin took a massive hit. As the press democratized knowledge, it was replaced by the vernacular language of each area, because merchants and common people needed books they could actually read.
And the printed word helped unify and standardize the spelling and syntax of those vernaculars.
Absolutely. Think of English or French or German. Before the press, spelling was chaotic and regional. A printer had a financial incentive to print texts that could appeal to the largest possible market, which meant adopting a standardized vernacular. This rise of standardized national languages is directly cited as a major cause of the rise of proto-nationalism in Europe.
Culturally and politically, the shifts were immense, but the impact was also deeply economic and scientific.
The press helped bring on the scientific revolution. It created a community of scientists who could easily communicate discoveries through scholarly journals. Knowledge became cumulative and collaborative.
And economically, the data suggests printing was associated with higher levels of city growth.
Well, the publication of manuals was transformative. Books teaching techniques like double-entry bookkeeping, the foundation of modern accounting, increased the reliability of trade. This paved the way for modern global commerce. The press literally created the instruction manuals for capitalism.
But for over 300 years, the basic mechanism of the press remained fundamentally unchanged. It was limited by human muscle.
Right, until the Industrial Revolution. That's when the search for truly unprecedented speed transformed everything.
By 1800, the demands for daily newspapers and mass education made the hand-operated wooden press obsolete. The first big improvement was structural.
Correct. The wooden press had weaknesses, wood warps. So the British inventor Lord Stanhope built a press entirely from cast iron around 1800.
And that iron frame provided immense integrity.
It did. The Stanhope press reduced the required physical force by 90% and doubled the size of the printed area. So it doubled the output from 240 impressions per hour to 480. A significant leap, but still limited by human muscle.
To break that barrier, you needed two things: power that wasn't human and continuous motion instead of stop-start.
And that takes us to the German printer Friedrich Koenig. Between 1802 and 1818, he solved both problems. He implemented steam power and, critically, he replaced the flat printing bed with the continuous motion of cylinders.
And this is where we stop talking about books for scholars and start talking about daily newspapers for everyone.
Exactly. The implications were immediate. In 1814, Koenig sold 2 of his first steam-powered models to the Times newspaper in London.
And what was the quantifiable leap this time?
This machine was capable of 1,100 impressions per hour, more than doubling the Stanhope press. They quickly improved it to print on both sides of a sheet at once. This was the definitive beginning of the mass audience newspaper.
That jump from 240 to 1,100 in just 2 decades is staggering. But even that wasn't fast enough. The final evolution was the full rotary press.
That came from the United States with Richard M. Hoe in 1843. Hoe abandoned the flatbed completely. He invented a press where the type was curved and mounted on a rotating cylinder, printing against another cylinder.
So the motion became continuous.
It's the ultimate mass production machine. Hoe's original design operated at up to 8,000 pages per hour.
8,000.
And by feeding paper from massive rolls instead of sheets, the speeds just became unbelievable. By 1891, state-of-the-art presses were producing 90,000 four-page sheets per hour.
Okay, let's put that entire journey into one final perspective. Hand copying. A few pages per day. The original Gutenberg press. 240 impressions per hour.
Koenig's first steam press jumped that to 1,100 impressions per hour in 1814.
And by 1891, the rotary press was achieving 90,000 four-page sheets per hour.
That is a speed increase that truly restructured human civilization.
What an incredible journey. We've seen how the press was a perfect confluence of existing technologies, perfected by Gutenberg's specific breakthroughs. The alloy, the hand mold, the oil-based ink, and this technological perfection led directly to the printing revolution. It democratized knowledge, standardized language, accelerated commerce, and provided the fuel for religious and political upheaval. It was the engine of change for the second millennium.
And that standardization, the fact that every copy was identical, is what gives us reliability. But here's the final provocative thought for you to consider. The sources mention that the printing press was immediately criticized, not just for its revolutionary potential, but also for allowing the rapid dissemination of incorrect information.
That's a powerful complication. We rely on the press for accuracy, but its speed is also what allows flaws to spread faster than ever before.
So given that the press made information standardized and ubiquitous, what impact does the ease of mass production and rapid instant circulation of standardized or potentially flawed information have on modern society, where digital printing and dissemination are not just fast, but immediate and universal?
The fundamental challenge of ensuring the accuracy of mass-produced knowledge remains, even though our press is now instantaneous. A question worth considering every time we click share.
Absolutely. Thank you for joining us on The Deep Dive. We hope you've enjoyed this look into Gutenberg's ingenious system and the world it created. Welcome back to The Deep Dive. Today, we are grabbing our passports and our theological dictionaries because we are stepping into the 4th century.
Specifically, the Roman Empire, 325 CE.
And this moment, spanning just a few months, is, well, it's perhaps one of the most consequential events that shaped the next 1,000 years of history.
It's the ultimate pivot point. I mean, think about it. Just 12 years before this, Christianity was legalized under the Edict of Milan.
12 years.
Right. So the church finds itself moving from the shadows of persecution to the sunlit and, frankly, probably terrifying halls of imperial power.
And that's where we're going today. We are diving deep into the First Council of Nicaea, an assembly called by the new sole Roman Emperor Constantine I in Bithynia,
which today is Iznik in Turkey.
Our mission today isn't just to, recap history. It's to really understand the high stakes of what happens when politics meets dogma. We need to pull out the absolute critical decisions made during this meeting, which ran from May to August of 325.
Precisely. This council was a total organizational overhaul. The accomplishments were multi-layered. You have the huge Christological issue, so the nature of Christ.
The big one.
The big one. Then constructing the Nicene Creed, which is foundational. Then they had to set a uniform date for Easter.
A practical matter, but a huge one.
The huge one for unity. And, crucially, promulgating the very first comprehensive set of standardized church laws, the canons.
And to set the stakes even higher, this wasn't just a one-off meeting. It established the whole format, the very idea of an ecumenical council.
It's the first of the 7 councils that defined early Christianity. And it was the first time they were forced to get down to the nitty-gritty, the technical details of Christology.
Moving beyond simple belief statements.
Exactly, into philosophical definition. The world had never seen anything like it.
And it all started because 2 guys in Alexandria couldn't agree on who Jesus was.
That's it in a nutshell.
Okay, let's unpack this. Nicaea wasn't called because everyone was getting along and decided to hold a conference.
No, not at all. It was called because there was a massive theological wildfire burning. And that fire was centered entirely in Alexandria, Egypt.
The Alexandrian controversy.
That's the core of the issue. A fierce Very public and highly disruptive dispute among the clergy there about the essential nature of God the Son, Jesus, and his relationship to God the Father.
And this wasn't new, right? It had been simmering.
It had been escalating for years, probably between 318 and 322 CE.
And the two opposing generals in this theological war were Archbishop Alexander of Alexandria and one of his priests, a man named Arius.
Right. And for the listener, you have to understand why this was more than just some academic debate. The stakes were the very definition of deity and salvation.
So what was Arius's argument?
Arius had a very systematic and, to a lot of people, a dangerously logical argument. He said the Father alone was truly eternal, unbegotten.
Okay.
Therefore, the Son must have been generated or created by the Father at some point in time. The Son, in this view, was a perfect creation, but still a creation, subordinate.
So Christ, while divine and special, didn't share the Father's absolute eternal nature.
Exactly. The phrase that just haunted the Nicene Fathers was the summary of his teaching. There was when he was not.
Wow.
It establishes a beginning point for the Son, and that puts him outside the eternal nature of the Father. It's a fundamental change in the relationship. If the Son was created, he wasn't truly God in the same way the Father was.
And Arius was quick to point fingers back at Alexander, right? He had a counter-accusation.
He did. He accused Alexander of falling into Sabellianism. This was a heresy that said the Father, Son, and Holy Spirit weren't distinct persons, but just three different modes or masks worn by a single divine being.
Like an actor changing costume.
Perfect analogy. Yeah. For Arius, you had to keep the Father and Son distinct to avoid that.
So if Arius is stressing subordination to protect the Father's uniqueness, how did Alexander counter that without falling into the Sabellian trap?
Alexander countered with this concept of eternal generation.
Eternal generation.
He argued that, yes, the Son was begotten by the Father, but this begetting wasn't an event in time. It was an eternal process, essential to God's nature.
So not a creation from nothing.
No, not ex nihilo. He was generated from the Father's own substance, and that maintained the Son's full co-eternity and co-equal divinity with the Father, while still keeping them distinct.
The local church structure clearly couldn't contain this.
Not even close. They tried. A local council of bishops from Egypt and Libya sided with Alexander, and, predictably, they excommunicated and exiled Arius and his followers.
But that just poured gasoline on the fire.
It absolutely did.
Oh.
Arius immediately used the communication networks in the Roman Empire. He didn't just fade away. He went out and built a coalition.
Gaining political and theological muscle.
He was highly effective. He traveled all over the Roman East and got support from really influential bishops like Eusebius of Nicaea and Eusebius of Caesarea. These were powerful guys.
And Eusebius of Nicaea had connections.
Huge connections. Yeah. Right to the imperial family. So once these key figures start taking sides, the schism isn't just in Alexandria anymore. It's fracturing the entire Eastern Church.
And that is what gets the attention of Constantine I. He's just become sole emperor in 324, fresh off a civil war. Why would he care about the specifics of Christology?
Pure pragmatism, political stability, imperial unity. He'd spent his entire reign consolidating power, and he saw Christianity as the perfect glue for his empire.
So when he hears about bishops and citizens fighting in the streets over theology,
the sources say he was greatly troubled. He saw this division as a direct threat to the fragile civil order he was trying to build. His goal was conquered. Homenoia.
It wasn't about God, it was about keeping the peace.
Exactly. His first move was almost naive. He sent an envoy with a letter basically telling them to just, stop it.
Who did he send?
He sent Bishop Hosius of Corduba, a very respected bishop from Hispania, with an imperial letter. And the instruction was stark. I do not wish you to leave schism or division of any kind anywhere.
Mm-hmm.
He basically called it a trivial dispute.
A noble request, but maybe a bit unrealistic for theologians.
Completely unrealistic. Hosius discovered very quickly that this was fundamental. He presided over a synod in Antioch that backed Alexander's position and excommunicated some Arians.
Which just hardened the positions on both sides.
Right. And when that failed, Hosius realized the emperor needed to intervene on a scale nobody had ever seen before.
And that prompts the call to Nicaea. But why Nicaea? Wasn't the original plan somewhere else?
It was, initially, Ancyra. But Constantine moved it to Nicaea for strategic and symbolic reasons. Strategically, it was much closer to his capital at Nicaea, so he could be there in person.
And symbolically.
He timed the council to coincide with the massive celebrations for the 20th year of his reign.
So this wasn't just a religious meeting, it was a massive state spectacle designed to show off the emperor's power as the new guarantor of Christian unity.
Absolutely. The theological meeting became a grand imperial event.
Let's try to visualize this. Grand feels like an understatement for this assembly in 325. How many people actually showed up?
The scale was, for the time, just staggering. Estimates ranged from 250 to 318 bishops. That number 318 became symbolic later, linking it to Abraham's household in Genesis.
But the real number is probably a bit lower.
Yeah, the actual lists of who signed the documents suggest something closer to 200 or 220 names. But you have to factor in the entourage, presbyters, deacons, assistants for each bishop. The total attendance was likely well over 1,000 people.
A logistical nightmare for the 4th century. How did they manage that?
This is where Constantine's power was essential. The emperor covered everything. The imperial treasury paid for all travel, all lodging, all food for the entire 4 months of the council.
And they met in the imperial palace.
In the palace itself, most likely in a massive rectangular basilica hall. It was a clear statement about the importance Constantine assigned to this meeting.
Now, geographically, the attendees were mostly from the eastern half of the empire, right?
Overwhelmingly. Mostly from Asia Minor, Egypt, Syria, the Greek-speaking half where the controversy was raging. The Western Latin-speaking church was barely there.
How few are we talking?
We can only confirm about 5 Western attendees. That includes Hosius and 2 presbyters representing the Bishop of Rome. This imbalance meant the whole debate was framed by Greek theological concepts.
Okay, we have to talk about Constantine's entrance. You mentioned it was theatrical.
Pure political theater meant to inspire awe. The historian Eusebius was there and described it. He said Constantine entered dressed like some heavenly angel of God, shining with the fiery radiance of a purple robe.
Wow.
Gold, precious stones. It was a deliberate, overwhelming display of divinely sanctioned civil authority walking into a religious meeting.
And gives his opening speech in Latin.
Right, which most of the bishops wouldn't have understood without translators. But he did join the debates later in Greek.
But he wasn't a voting member. What was his actual role?
He was the convener and the enforcer. He made it clear he would defer to the bishops on doctrine, but his goal, his entire purpose for being there, was to achieve unanimity and concord. He was the peacemaker with an army.
If the emperor wasn't running the debate, who was?
The consensus points to Hosius of Corduba. He was Constantine's trusted envoy, seen as neutral and highly respected.
And the debates were modeled on the Roman Senate.
Yes, very structured. And interestingly, one of their first bits of business wasn't even about Arius. It was about who could even participate. They had to decide if bishops who'd been excommunicated for Arian sympathies, like Eusebius of Caesarea, could even have a seat at the table.
What did they decide?
They decided they could, but only after providing a credible statement of their own orthodoxy.
And beyond the Arian issue, they also had to deal with the Meletian Schism. Remind us what that was.
That was an internal power struggle in Egypt. It was about a bishop, Meletius of Lycopolis, who started ordaining his own clergy during a persecution when the Bishop of Alexandria was in prison.
So when the official bishop's successors took over, Meletius refused to recognize them.
Exactly. He created a rival church structure. So it was a schism, a break in unity, not a doctrinal heresy like Arianism.
And Constantine needed to clean that up too.
He needed the Egyptian church, which was the intellectual powerhouse of the East, to be unified politically as well as theologically. It showed the council's mandate was broader than just one issue. It was about creating universal church order.
So after all the pomp and procedure, they get down to it. The Nicene Creed. Why did they need to write a whole new creed?
The driving need was for clarity and standardization. For the first time, they needed a definitive test for who was in and who was out. Before Nicaea, you had simpler creeds, like the Apostles' Creed in Rome.
But they weren't specific enough.
Exactly. The Arian crisis showed that those simple summaries could be interpreted in different ways. They needed a theological litmus test. And the Nicene Creed became that document.
The real power of the creed is in its anti-Arian language. What were the specific phrases they used to shut Arius down?
It's like a theological toolkit designed specifically to disassemble Arianism. First, they proclaim Christ's full divinity, light from light, true God from true God.
Leaving no room for a lesser created divinity.
None at all.
Yeah.
It puts him on the exact same ontological plane as the Father.
And the second point directly attacks the idea that Christ was a creature.
Absolutely vital. The Creed insists Christ was begotten, not made. Arius argued that begotten meant made. The Nicene Fathers drew a sharp distinction.
How so?
To be begotten means to come from the very substance of the Father. To be made means to be created from nothing, ex nihilo, like a creature. By saying not made, they directly refuted Arius's core premise.
Which brings us to the centerpiece, the Greek term homoousios.
Homoousios, meaning of one substance with the Father. This was the definitive, non-negotiable roadblock for the Arians.
Why that word specifically?
It ensured that the Father and the Son shared the exact same divine essence, or ousia. Without it, you could still argue Christ was just like the Father in substance, but not identical. This word closed that loophole.
And it's fascinating that Constantine himself might have suggested it.
Yes, Eusebius of Caesarea, who was initially very hesitant about the term, said Constantine suggested it. Now, whether Constantine fully grasped the philosophical depth is debatable.
But he understood its political power.
Oh, he understood it was a definitive, unifying marker that was very hard to refuse when the emperor suggests it.
But the term was controversial even for some of the Orthodox bishops, wasn't it?
Highly controversial. It immediately created ambiguity and set the stage for the next 50 years of conflict. Some worried it sounded like Sabellianism, blurring the Father and Son together.
So the conflict didn't end.
It just changed the vocabulary. It was a victory, but one that took decades more to fully define.
And to make sure there was zero room for misinterpretation, the creed ended with anathemas, explicit rejections.
The kill switch for Arian theology. They explicitly listed claims that were outside the faith. The first one targeted the idea that Christ had a beginning.
There was when he was not.
They rejected that completely. This mandated the Son's co-eternity with the Father.
And the second anathema.
It rejected the idea that the Son was mutable or subject to change. This is a philosophical point about perfection. If the Son was a creature, he could potentially change, even sin. This affirmed his absolute divine immutability.
So once the creed was signed, Constantine stepped in to enforce it.
Instantly. The moment the bishops passed their judgment, Constantine turned it into a civil sentence. Arius and the two bishops who refused to sign were excommunicated by the church.
And then
Immediately banished into exile by imperial decree.
And he went even further, trying to erase the heresy itself.
He did. He ordered all of Arius's works to be confiscated and burned. He labeled his supporters enemies of Christianity, and that's the moment.
What moment?
The moment heresy stops being just a spiritual danger and becomes an act of treason against the Roman state, a precedent that would last for centuries.
So, moving beyond that monumental theological fight, Nicaea was also a huge administrative meeting. Let's talk about the practical stuff, like setting the date for Easter.
Right, the Paschal computation. It sounds simple, but it was a huge source of friction. Historically, Easter was tied to the Jewish Passover, Nisan 14th.
But Christians were growing dissatisfied with that system.
Why? The main issue was that the Jewish calendar sometimes set that date before the spring equinox. For Christians, the resurrection had to happen after the equinox, symbolizing new life.
Plus, everyone was celebrating on different days.
Exactly. It was celebratory chaos. So the council resolved it by endorsing a fully independent Christian calculation. Easter had to be on a Sunday after the spring equinox and always after the Jewish Passover. It created uniformity.
Now, let's go back to the Melitian Schism. What were the specific measures they took against Melitius?
They were designed to look lenient, but were actually devastating to his authority. Melitius got to keep the title of bishop, but he was forbidden from ordaining anyone or exercising authority outside his own city.
And his existing clergy.
They were effectively demoted.
Yeah.
They had to be reordained by an Orthodox bishop and had to yield precedence to clergy ordained by Alexander's side.
So he kept his hat, but lost his power. Did it work? Did it heal the schism?
No, and that's the great irony. The measures failed completely. The Melitians felt marginalized and later allied themselves with the Arians. They became some of the fiercest opponents of Athanasius, Alexander's successor.
So much for peace in Egypt.
Not at all.
Finally, let's talk about the bedrock of church administration. The 20 canons.
These were the first widespread rules of church law. They established fundamental structures. For example, Canon 4 standardized how bishops were ordained.
What did it say?
It said you needed at least 3 provincial bishops present, and the whole thing had to be confirmed by the metropolitan, the senior bishop of the province. It was about curbing unauthorized appointments.
Okay, let's spend some real time on Canon 6, the one about jurisdiction. It's been debated for 1,700 years. What did it confirm?
It confirmed the ancient custom that gave huge regional jurisdiction to the bishops of Alexandria, Rome, and Antioch. It essentially codified the existing power structure.
And the disputes are all about how you interpret the reference to Rome.
Exactly. The Catholic interpretation tends to see the mention of Rome's custom as proof of Rome's superior confirmatory role. that the authority flows from the successor of Peter.
And the Protestant interpretation.
They argue the opposite, that Rome was mentioned just as an illustration, that the point was to confirm that all three great bishops, Alexandria, Rome, and Antioch, were on equal footing, each presiding over their own traditional territory.
And there's a third view based on political geography.
Right, which is crucial context. The civil administration was complex. Rome and Milan shared jurisdiction in Italy. Antioch and Alexandria were both in the Diocese of Oriens. So the canon might have just been using Rome's way of managing its complex civil diocese as a precedent for how the others should manage theirs.
It grounds it in the reality of the time, not later arguments about primacy.
Precisely.
Beyond that high-level stuff, the canons also addressed clerical life. What about Canon 17?
Canon 17 explicitly prohibited usury among the clergy charging interest on loans. It was a significant moral line in the sand, ensuring ministers didn't profit from the hardship of their parishioners.
And the final one we should highlight, Canon 20, which is about worship posture.
Right. It's a fascinating detail. It prohibited kneeling on Sundays and during the entire season of Pentecost.
Why no kneeling?
Because kneeling was seen as a posture of penitence, of sorrow. Standing was the posture for festive, joyful prayer. The canon was about ensuring the celebratory nature of the Lord's Day was reflected in the physical posture of the worshipers across the whole church.
Okay, before we get to the aftermath, we have to clear up some persistent myths about Nicaea. The first is maybe the most famous. Did the bishops at Nicaea select the books of the Bible?
Absolutely not. This is a complete fabrication. There is no record of any discussion about the biblical canon at Nicaea. None.
What about the story of books falling off an altar?
Pure fiction. That story didn't even pop up until the 9th century and was popularized much, much later by people like Voltaire. The canon was largely settled in practice long before 325.
Misconception number 2. Did Nicaea finalize the full doctrine of the Holy Trinity?
It did not.
Yeah.
Nicaea was laser-focused on the Son's relationship to the Father. The term Trinity was already in use, sure, but the nature of the Holy Spirit was barely touched upon. That wasn't really defined until the Council of Constantinople in 381.
And the third myth is about Constantine himself.
Right.
Given his deep involvement, he must have been a baptized member of the church by this point.
Also incorrect, and it's a critical detail. Constantine was not baptized until 11 or 12 years after the council, right on his deathbed.
Why wait so long?
It was a common, if maybe cynical, practice. The belief was that baptism washed away all previous sins. By waiting until the very end, he hoped to be absolved from as much sin as possible from his long and often violent reign.
Okay, so let's confront the immediate reality. The council achieved a kind of forced unanimity. Was the theological war over when everyone went home?
Far from it. The problems were emphatically not solved. Nicaea was more like a temporary truce enforced by imperial muscle. Arianism didn't disappear. It continued to spread.
And the political fallout shows just how fragile that Nicene victory was.
It was incredibly fragile. Arian bishops, especially Eusebius of Nicaea, who was a cousin of Constantine, immediately used their court influence to get back into the emperor's favor.
So the heroes of Nicaea, the Orthodox defenders, they suffered for it.
They suffered immediate and harsh retribution. Within just a few years, the key Nicene defendersmen, like Athanasius, who succeeded Alexander, were systematically targeted, deposed, and exiled.
Between 330 and 336, so the very men who defined orthodoxy were exiled by the emperor who enforced it.
Exactly.
And the final, crushing irony comes back to Constantine's deathbed.
It's the ultimate historical twist. In 337, Constantine, the man who called Nicaea, is finally baptized, and the man who performs the sacrament.
Let me guess.
The recently reinstated, staunchly Arian bishop, Eusebius of Nicaea. It just perfectly encapsulates the complete lack of immediate peace that followed the council.
This has been an absolutely fascinating deep dive. It's impossible to overstate the influence this one summer meeting in 325 had on the Christian faith.
Profound is still an understatement. Nicaea established the precedent for ecumenical councils. It provided the foundational definition of Christology, it standardized the calendar, and it formalized church law.
But I think most fundamentally, as we've discussed, it set this powerful and defining precedent for the relationship between the church and the state.
Yes. Nicaea demonstrated the power and the challenge of trying to unify belief across an empire. It solidified the practice of using the state's political and military muscle to enforce what the bishops deemed orthodox. That link between throne and altar defined history for centuries.
So we've detailed the triumphs, but the post-council reality, the continued conflict, the strength of Arianism, the swift exile of the creed's own defenders, it all raises a powerful question for you to consider. Did the First Council of Nicaea truly achieve peace? Or did it simply formalize the starting line of a much larger, more protracted theological war?
A conflict that, in many ways, would consume the empire for the next 50 years.